Yes, sir, Rathod, sir. We are ready to go, sir. Right.
Okay, okay. I, Dr. K.B. Rathod, Head of Mechanical Engineering Department from RNG Patel Institute of Technology, Bardoli, welcomes you all on the 11th webinar of the Mechanical Engineering Department and 51st webinar of the College of Series 2 under SSIP cell. The topic of webinar is Computational Fluid Dynamics, Introduction and Application. And to present such an important topic, we have with us Dr. Chandrakant Sonawane, Associate Professor in Mechanical Engineering Department from Symbiosis Institute of Technology of Symbiosis International Deemed University, Pune, Maharashtra. Dr. Sonawane did his PhD from IIT Bombay in the year 2013 in the field of computational fluid dynamics. His area of interest is computational fluid dynamics, thermal engineering, advanced fluid dynamics, heat and mass transfer, air conditioning and refrigeration, etc. Dr. Sonawane is having 17 years of experience, total working experience. Out of 17 years, he has 12.5 years of teaching experience and 4.5 years of research experience. Out of 12.5 years of teaching experience, he taught at Aerospace Engineering Department in IIT Bombay as a full-time teaching assistant from 1st January 2008 to 24th June 2012, almost 4 years and 6 months. And right now working as an associate professor in Mechanical Engineering Department at Symbiosis Institute of Technology, Pune, since 15 February 2016 to till that, where he has also worked as an NBA coordinator for 27 months. During his tenure of working, Dr. Chandrakant has published 51 technical papers. Out of 51 technical papers, 15 papers are published in international reputed journals, one paper in national journals, 26 in international conferences, and 9 papers in national conferences. Dr. Sonawane has also published one book along with Dr. Joshi Mandal on incompressible fluid flow computation, a HLC SE-based numerical approach, published by Lambert Academic Publishing, Germany. He has also completed 2 research and development projects as a principal investigator, one from DST, Government of India, New Delhi, of the amount 18 lakhs fund, and another of 1.5 lakhs funds from Symbiosis International University, Pune. There is just still a lot more to say about Dr. Chandrakant Sonawane, but looking to time constraint, I have to curtail down his biodata, and I would like to hand over the sessions to Dr. Sonawane. Over to you, sir.
Okay. Thank you very much, sir, for a nice introduction. Okay, so I think we'll start with the session.
Yes, definitely. First, you share your screen, please.
Is my screen is visible?
No.
No, sir. Your screen is not visible.
Okay. I will share again.
Yes. Sir.
Okay.
Yeah, it's coming.
Okay.
Yeah. Okay. Now it's good.
Okay. Thank you very much. Good afternoon, all.
Yeah.
So today I will talk on computational fluid dynamics, where we'll try to see the introduction, why the topic is important particularly, and its applications. And I'd also like to share with you the various applications where we can do, and there are still future aspects where there much has to be done. Okay, so to start with, we can have the first question: what is this CFD particularly, and what is its objective? So, as the name suggests, computational fluid dynamics. So, we already studied the fluid mechanics as well as the engineering mechanics in our second year, first year. So I would like to break down the term computational fluid dynamics. So the first term will go with the fluids. So we know the fluid mechanics, okay, where we try to study the all significance properties, behavior, like kind of the fluids stuff. The fluid, to whom we decide the fluid, or to whom we say that it is a fluid, is a liquid, gas, or in layman definition, what we say, the fluid is a substance which has the ability to flow. Okay, and if you try to see as far as technical definition is concerned, so fluid can be a substance which continuously flow or which continuously deform under the influence of applied force. The applied force, however, it may be a very small amount, no matter. So if something is flowing by the application of some force, so we can term as a fluid. Second term, dynamics. Dynamics, we know that it's opposite to static. Static, stagnant. Okay, so dynamics usually talks about everything is moving. When we say moving, so the movement does not happen by its own. There has to be something, either say usually is a force which either pull the stuff or the fluid and make the motion happens. Hence, the dynamics is study the velocities or the moving stuff by the influence of forces. Then we have the computational. It's obvious when I'm trying to use the computer to study the fluid which are under motion along with the all forces, so that we usually known as computational fluid dynamics. Now we know that in case of fluid mechanics, if you remember the lab experiments where we conducted the flow through pipe, okay, then metacentric height, then I think Bernoulli's apparatus, Venturi, orifice, all this kind of experiment, where we prefer to have the experimental evidences to sort out the either their say any kind of coefficient finding or any kind of analysis. So typically whole fluid mechanics, or I will say that whole the mechanics is typically based on the experimental work. So experimental work is highly preferred. However, we cannot do the experiment for all kind of cases. There are simple stuff where we can do the experiment and we can get the data. However, for a scenario like, say, if I have to example of, say, when the bomb blast, okay, what happens? So this kind of simulation is very tough. Getting experimental facilities for this kind of uh, say experiment is very tough. Then what we do? We try to assume something. Say for example, usually what we do in our fluid mechanics or the heat transfer kind of case, we try to assume a number of assumptions like 1D, 2D, or even say without viscosity or no friction. This kind of things we try to apply and try to sort out or try to simplify the equations, the models, such that we can obtain what you call as analytical solutions. So that we usually known as analytical fluid dynamics. However, when we are not interested in such kind of analytical experiments, and when it is very difficult to go with the experimental kind of stuff, so there comes in picture the computational stuff. Hence, CFD is feasible. We can say that mainly due to the only one advancement that we know that today's high-speed digital computers are there. So even our laptops and all these things we get i7, i8, i10, whatnot. Okay, so we have a Right now, we do have a good amount of high-speed computer with us, and using these computers, we can try to solve the fluid dynamics problems. What I want to say that what we are trying to solve, I am saying computer simulations we can do and predict the fluid flow phenomena. Fluid flow, how to predict fluid flow phenomena? So if you remember, in case of fluid mechanics, usually what we say start with, consider a infinitesimal small volume, okay, then get some differential equation, then integrate it, and then try to solve it. Okay, so it is very similar process. In case of CFD, usually we get those kind of continuous fluid flow with differential equations, and these differential equations are mainly the partial differential equations, because we do have the dependence on not a single parameter, but the number of parameters, say x direction, y direction, z direction, along with the time. Okay. Then we try to discretize this problem, and we try to get some solution using some computational techniques, popularly known as numerical techniques. Many of you come across number of numerical techniques where the subject is numerical methods. Okay. Don't worry, I am not going to show you the whole equation stuff in my presentation, but I want to make sure that you should know what kind of equations we are going to use and who proposed the equations basically. So what we solve is the conservation laws, mass, moment, energy conservation laws, and these are the two great scientists who given the fundamental equation for fluid dynamics, the Navier and the Stokes. So, and on the honor of their name, we do have a Navier-Stokes equations in case of computational fluid dynamics. So, I will not show you the equation right now. When you get the time, please go to the Google and try to search for the Navier-Stokes equations. So it will basically a partial differential equations, and there are many useful stuff that you will get it. Okay. So once we're done with the equations, so the next question, why I use CFD? Do I need to go? Why I need to solve those partial difference equation? Why I should go and do all those kinds of software and all likewise? Okay. So do I enough motivated to use CFD? Okay. So here is your answer. Why use CFD? So CFD is mainly used for two purposes. First one is analysis and design, and second is knowledge and exploration of the flow physics. As far as analysis and design is concerned, simulation-based design instead of build and test. Okay. So usually what we do in case of experiment, we build, test. If it works, then fine. If it not works, we'll try to rebuild. So making a number of prototypes. Okay. So the cost of prototype and the cost of testing those prototype is very huge. And the main purpose, the time lapse in making the prototype, testing the prototype is huge. Okay, instead of that, what we can do, we can use CFD simulation and replace. I will not say completely replace, I am saying replace 90% of time consumed as well as the cost consumed by the CFD. Hence, it is more cost effective as well as more rapidly than with the experiments. Remember that I am not replacing the experiment completely with CFD. At the end, when you approach to a final kind of configuration, I will recommend you should build that and test it. Okay. So instead of building and testing the say 10, 20 prototype, you build one or two only. Okay. The remaining can be tested using CFD. Along with that, CFD will also provides the high fidelity database for integration flow field. If you remember the flow through, say, a pipe, the Reynolds experiment, what we usually do, we take a reading at the end of the pipe. You know? However, if I want to find the velocity at the middle of pipe, if I want to find the pressure at the somewhere, that information is not available with me. Okay. So when I do CFD simulation, so whole data starting from the pipe inlet to the pipe outlet, whole range data is available to me. Okay, that's why I am saying CFD provides the high fidelity database for interpretation of topics. Next, we can have the simulation of flow fluid phenomena that are difficult to be measured by experiments. Okay. So I have already given one example, like say hazards, where you have a explosion modeling, radiation modeling, pollution modeling. So this kind of experiment, it's not easy to build. Okay, and they are also not cost effective. The testing costs for those are very huge, and there is a lot of risk involved by to test such kind of hazardous phenomena. Along with that, we can do the scale simulations. Say, for example, we can have the full scale ship model, airplane. So you can do the simulation of flow for Titanic. Okay, it's a huge ship. Or you can also try the simulation of a submarine. Okay, that's a huge. If you want to test the submarine or the aeroplane or the Titanic, where you have the facility for testing, the experimental testing. Okay, so this kind of all kinds of impossible, say, experimental things can be possible by using computational things. Then we can have the physics like weather predictions, planetary boundary layers, then stellar evolution. So weather prediction, huge amount of area need to be tested. Say for example, even if you want to do the what is the prediction of the that particular, just recently we have that Nisarga cyclone, hit the Maharashtra and Gujarat. So how it is going to be move ahead, whether it will go to Maharashtra, it will go to Gujarat, or it will go to some the northern part of, say, Pakistan. Okay, so that predicting this kind of model, it's quite tough. Okay, and you need to test all those things if you want to go experimental things. So it's really impossible. So what we do, we try to predict the flow conditions using CFD simulations. Okay, when I want to say that the physics, so usually what our fluid mechanics says, so we have a number of kind of flows. Okay, fluid flow can be have a viscous flow, it can be an inviscid flow. In case of viscous, I think you come across laminar kind of flow, turbulence kind of flow. We do have a internal flows like a flow through pipe, flow through wall. We do also have a external flows like flow over ship, flow over aerofoil. When you talk about inviscid, we have a number of options. Like either we can go with the inviscid compressible or incompressible, as well as I can have the viscous compressible or incompressible. The compressible flows are mainly when the density changes are appreciable, whereas incompressible flow where density is constant. If you remember, we usually come across the non-dimensional analysis, which will provide us a very useful kind of the non-dimensional numbers. I hope you come across large number of non-dimensional number like Reynolds number, which is very popular in case of viscous or inviscid laminar and turbulent flow, as well as Mach number, incompressible or compressible, supersonic, hypersonic, then sonic, subsonic, all this kind of conditions, these are being predicted by this kind of non-dimensional numbers. Why I am showing all these numbers to you? It's a clear indication that when we do some kind of simulations, they are mainly dependent by this kind of the fluid physics. Okay, And these fluid physics are essentially are can be predicted by this kind of non-dimensional number. Say for example, if the flow through a pipe, if the Reynolds number is more than 4,000, we usually say that it's a turbulent flow. Correct. So if I know the non-dimensional numbers, so it's easy for me to predict that particular kind of flow. Okay. Hence, the knowledge of non-dimensional number, which is again a concrete base for experimental uh, fluid mechanics, is a very same base for the computational fluid dynamics. The difference is that we are only doing at the what you call as computational facility. So sometime the CFD is also known as the virtual wind tunnel. Okay, I think you come across the wind tunnel where we try to see or try to model the flow over aerofoil, flow over sphere, and likewise. Okay, so this is a very similar to the wind tunnel. However, it is an what you call as artificial wind tunnel, or we can say that it's a simulated based wind tunnel. Okay, so this is one a simple what you call as the design cycle usually we try to have where CFD fits and where I can have the this kind of, if you remember the machine design, or where we try to do the CAD and CAM and likewise. So CFD is essentially a part of what you call as computational assisted engineering. Okay, where we can have the CFD, computational fluid dynamics, CSM, where it's a computational structural mechanics. We can also have a CAA, it's a computational aeroacoustics, CEM, computational electromagnetics. Okay, so CFD help us in a design phase. Okay, it try to help us designing a something or evaluating its performance, whatever you have designed. Okay, so if you have something generated using CAD, so you can do the CFD simulation along with the APM simulation using the CFD. Okay, okay. So when I say the CFD, let's take one example. This is a what you call as direct numerical simulation. Okay, where I am not assuming anything. So this has been generated by the Jimenez and the co-worker at Almaco library, lab particularly. So this is a flow through a channel, and you can see that how the fluid is look like. The fluid is look like it's some kind of jumps. Okay, what we see in case of that Lifebuoy advertisement. Correct. So the fluid essentially flows, okay, just like a jumps. So these jumps are usually known as the eddies. Okay. If you want to give the details of this flow, so this is a DNS simulation obtained at Reynolds number of 47,500, and they have used the grid size. Okay, NX by NY by NZ. So 1048 cross 385 cross 1556. So the mesh point you can see is almost 1.22 10 raised to 9 mesh points. Okay. The time required to calculate this kind of flow is 10 raised to 6 processor hours, and they have used a 384 processors. Another example. This is a turbulent flow through again one more channel uh, obtained by Hoyes and Jemers particularly. So here again, you can see that the flow is flowing like a jumps. Okay, these are called as eddies. So The details is the flow through channel having a Reynolds number of 100,000, and they have used the mesh NX, NY, NZ of the order of 7.9, 10 raised to 9. Okay, so the time required for this computational is again in the order of 10 raised to 6 hours, and they took almost 6 months for a single simulation using that Mare Nostrum supercomputers in Barcelona, where they have used 2100 processors. Okay, getting one simulation you need 6 months. Okay, so this kind of flow where you are able to capture the each and every particle that in terms of eddies, it will provide you the direct simulation of that particular real flow. Okay. The one major question, do we need such kind of simulation right now? The answer is no. This simulation is capturing the flow as well as the effect of flow. Okay. So here again, the flow as well as the effect of flow. The effect of flow, I want to say that the shear stress and the pressure and the velocities, what is being done by each and every particles, each and every by that particular eddies. However, we are in actual practice, we are not interested to capture the actual fluid flow. Rather, we are interested to capture the effects of that flow. Okay, why the flow is caused, why the heat is being transferred. So we are interested to calculate the effects rather than the flow. Okay, so these two particularly, the direct numerical simulation is what I have shown you is mainly is in future where you can explore more. In near future, we can go and obtain more and more computational power. So we can go and handle this kind of large number of meshes, and hopefully the number of time required, the 6 months may reduce. Okay. However, CFD has been very popular almost in every field. You name the field, the CFD is there. Okay. So particularly if I want to see what are the applications of computational fluid dynamics. So here is the list which I found, which I taught usually in my classes. And this is not a complete list, but this is sufficient to inspire you to join CFD. So CFD is basically brought up by the aerospace industries. They need a lot of simulations on the aircraft, wings, missiles, and likewise. Then from aerospace industry, then it is being captured, or I will say it is being popularly used by almost all kind of industries, mostly the automotive industries. Then we do have a very large amount of appliances. Nowadays, biomedicals are the one of the biggest, you can say, the users of computational fluid dynamics. Then chemical processing, all kinds of chemical plants, they try to use this kind of CFD. Then HVAC and refrigeration systems. We do have number of heat exchanger, evaporator, fans, blower, compressor, all kinds of applications is been included in HVAC. Hydraulics. Okay, we do have a number of hydraulics applications, mainly in case of the industries, manufacturing industries, marine applications. In case of marine application, we do have a submarine, boat, ship. Then we can have the underwater vehicles, the flow of even the rivers, or the flow of even we can say that the flow of the sea. Now, the Tyndall energy people are now they are very much interested in the CFD simulations. Oil and gas. Oil and gas people they try to use is for the flow of oil and the gas of oil through pipes and number of applications. Power generation, we know that traditional power generation or non-conventional power generation both are have a lot of applications of CFD. And this is one of the again getting the popularity in case of sports. Sports maybe in case of that if you take an example of the cricket ball or the swimming or even you can have the football, all this kind of they try to predict how the things will propagate, how we can reduce the friction, how we can in case of say swimming, how we can have the clothing structure can be designed so that the friction can be reduced. Okay, let's see the one by one applications in slightly detailed manner. Okay, so I do have some kind of a simulation with me, which I mainly taken from the YouTube. Okay, thanks to the YouTube. You can go and refer to those simulation. Right now, I will try to show you something. So, the as I told you, aerospace industries. So the first figure, F-18 store separation. So basically, CFD will try to predict how the that F-18, particularly you can say that the bombs, or it may be some kind of supplies which we need to give it to our say, soldiers which are at the ground where we cannot reach by say for example by the bus and the trucks. So usually they drop this kind of uh, store from the a plane. This can also have the civilian application where we do have a flood, and this kind of things has been again dropped. The food, the medicine is being dropped from the helicopter, from the plane to the people who are in trouble and standing mostly on their you can say that okay in their balconies. So where to drop all this thing, what is the fluid friction, and how they can be get accurately dropped at the location where we want to drop it. As far as the wing is concerned, so wing body interaction. So as we know that the aeroplane wings they flap during landing, during takeoff, or during the maneuver. So we have to go up or to go down. So this kind of the wing body interaction, how we can generate a lift, how the drag can be minimized. There is a minimum amount of lift that need to be maintained there to have this kind of the plane is in motion. The CFD is also popularly used in the what you call as the rocket launching or even for the re-entry vehicles. Okay, so this kind of can have one figure here where the rocket things when it gets the pressure distribution is there and how the pressure contours, what amount of pressure contours has been developed for the this kind of what you call as a simulation. If you remember the incident happened with the Kalpana Chawla, okay. So we know that particularly their ship is crashed because of the what we call as a small hair crack was there in their ship, and when they re-enter, the heat, the frictional heat when they are entering in the atmosphere, that get okay conveyed into the ship. They burn whole the ship, and then it's busted. Okay, so this kind of simulation will help you out how we can have the proper design of what you call as either aircraft or wing or likewise. Okay, let me show you some. I have some YouTube. a video with me. Okay, so this essentially shows how the contours. Okay, so this is a simple wing. What we try to say that. Okay, so when the wind fluctuates, okay, so it's oscillate and fluctuates again. So what kind of contours, what kind of shading it has been created, and likewise. I can also have some kind of simulations. This I have taken from the what you call as DUSAT. Okay, DUSAT systems. You can go and check. Okay, you can go and check this kind of systems. So here is a okay, this kind of simulations. Okay, whatever is happening over the wings. So indirectly, I'm also providing the popular companies who are working in CFD. Okay, so let's watch it again. I can also have this helicopter simulation. This all kind of things are available on YouTube. Okay, when the wing rotates. Okay, so what kind of contours? So how we do the CFD, how the flow is being generated, how the lift is being created. So this all will help us to design a proper what you call as helicopter. Not only front wing but also on the back wing, which will help us for the maneuvering purpose, the gyroscopic things. Okay. So aerospace industry is basically okay, I do have something for flow through aerofoil, which I want to show it to you. Okay, this is a okay. This is what happens when it's okay flap and pitch. So you can see that this vortex shading is created, and this vortex shading is mainly possible for creating lift, drag. There are certain more phenomena. I will recommend please go to the some CFD online, or even you can go through Wikipedia, and then where you can get this kind of nice simulations. And I hope it is sufficient to motivate you how we generated this kind of these things. Okay, so essentially it this kind of simulation provide us what we call as the design purpose. Okay, so how to design a wing, how to design say the that store separation, the flow over a wing, all these kind of things is being okay is used nowadays. And there are a number of lot of companies are they are investing lot of R&D things in case of CFD. The second largest is the appliances. Right now, you name the appliances, particularly all appliances industries nowadays they try to do CFD. I have taken one simple example of this is a no cross refrigerator by the Bosch and the Siemens, where they try to predict the flow through this some kind of trays and this kind of what you call as the fridge. Okay, I do have a simulation with me for a fridge. Okay, let me show it to you. Okay, as you open a fridge, how the cold air, okay, it get dropped down, and what will happen? Okay, I will try to replay. So once you open a fridge, then cold air. This is all commercial simulations. Okay, I can show you the simulation done by my student as well, but I hope you will enjoy more if I show you some industrial examples, mainly by the popular companies. So that will help you, that will encourage you a lot. This is done in Simulate Explo software, particularly. Okay, so there are lot of companies are there which are okay, which are involving a lot of R&D, as well as they try to have a new design. Nowadays, you come up with the like that ulta freeze, you know, where they kept the refrigerator at the down location and the all other stuff, or the evaporator is at the bottom and the rest freezes at the top location. So instead of using natural convection, they try to use the forced convection. Okay, and by using poor convection, they are saying the BMR is high. Okay, that one need to check. But as far as appliances are concerned, okay, for better designing, like say washing machine, how the cloth can be clean. Then we can have the mixer, how we can design the blades such that the flow in the mixer, or remember when the chutney has been made, how the flow will come again to the center instead of getting out. Okay, so although the flow get out, and it should come back to the again center so that the continuous process can be happen. So how the fluid is flowing through that particular say mixer and all those things, that can be simulated. Okay, and it has been doing, a lot of companies are doing. Then we can also do simulation through the what we call as chimneys. Okay, chimneys, a lot of people are using chimneys. So the home chimney, the particularly, so we can use say how the particularly the air over a gas can be get sucked properly, and how it can be cleaned, how the it can remove the oil, and how we can improve the kitchen condition particularly. Okay, there is one more important that appliances, if you go and check for the cooling of electronics. Okay, this is the biggest issue. Your laptop gets heated, your TV gets heated, okay, or even desktop get heated. So how we can achieve, how we can simulate such that we can design a better uh, say appliances for our home conditions in a lower cost. Okay, next, CFD has been popularly used by what you call as the automotive. Okay, I don't have to tell you about the automotive much, because the flow over car aerodynamics, although I have given you the simple example of what you call as car, but even we can have the racing cars and all likewise. Okay, even we can have the undercarriage aerodynamics, how the flow is okay, is going to flow through this kind of car below particularly these things, how the say coolant from the engine coolant box is being circulated, how the oil is being circulated. Okay, that is mainly the engine cooling and can be done. As far as the interior of car is concerned, so we do have a lot of simulations where we can have a better ventilation design, how the AC can be designed, how where we can put the AC vent so that particularly the not only driver but the passenger who are sitting at the back end, they can be cooled properly. Nowadays cars are trying to use the multi vent. They have a vent at the driver location as well as they have a vent at the backstage. Okay, so this is one of the improvement what we are trying to do. So you can try how the say particularly car cabin is being effectively cooled. Okay, and can be used. Another another popular field is a biomedical. Okay, so as I told you, biomedical things, the flow through what you call as the blood pump. Okay, so the artificial heart, flow through heart, flow through arteries. Okay, this has been popularly even flow through brain, flow through small what you call as this kind of this spinal cataracts. Okay, so how the blood is flowing, it will help us to design a proper what you call as say in case of heart surgery, say the proper stent can be designed, or even some part is damaged in case of heart or the arteries or get blocked. So how we can remove those things by using external stain or something like that can be done. Okay, please remember that you cannot do the experimental stuff on the human body. You never get experimental testing in such kind of flow. How we can have the experimental testing of heart of a human, say, or even say any animal? Okay, and you can test what is the pressure after the heart, what is the pressure behind the heart. We do have external devices. Okay, I agree. However, for each and every case, but we cannot go and do these things. So for the say heart attack patient or heart patient, we do need to do and check it for this using this kind of simulation by predicting some kind of flow pattern. We should able to predict this which has say 10% blockage, 20% blockage, 50% blockage. So this kind of data is possible. People are doing these things using image processing as well as using the this kind of CF distribution combination. We can do a lot of things is going on. This is one more example where you can have the eye cataract. Okay, so the temperature and natural convection of the current in the eye. Okay, following the laser heating particularly. So laser treatment is basically used to for the retina and all those thing operations. So how the laser heating can be used? How what will happen? So all these kind of applications can be have lot of scope in future if we go with the CFD simulations. Chemical processing. Chemical processing is being popularly used. So for either in case of where we keep our say chemicals, mixing of chemicals, or by using some kind of process like how the say twin screw extruder flow modeling can be done. So by extracting the chemical or by injecting the chemicals, so there are number of reactions happens, endothermic reaction, or the chemicals may get diffused to each other. So all kind of including chemical reactions we can do the CFD. So that is possible. As far as the HVAC systems are concerned. So this has been popularly nowadays used by a lot of air conditioning suppliers. Say for example, the workstation ventilation. Okay, so almost now we see that all IT companies they hardly have any single window. Okay, and some location we have very cold, some location we have very hot. Okay, so this happens because we have not placed the vents of the AC by knowing the actual heat load. Okay, the we usually our traditional approach that at certain distance we should have certain amounts of say vents. However, If the peoples are not present there, if the load is not there, if the computer and all these are shut down there, so the heating load is not available. Hence, that place may get more colder. Okay. In such kind of scenario, the AC vent should be automatically get shut off. However, this kind of design has been not implemented since last few years. Now they are modifying the inlet and the opening of that particular vent as per the load conditions. Okay. So as far as predicting the workstation ventilation is concerned, or as far as how much is the VOC vent emission is concerned. Okay. So whether how much percentage of CO should be allowed, how much percentage of fresh air should be allowed. So this may create a nausea when the people works n number of hours in that particular room. They start creating nausea. Okay, some may feel allergic, some may feel a drowsy because of the CO kind of stuff. Then simulation of particularly as far as the the vent where we flow the conditioned air as well as flow where the return ducts are come. Okay. So even traditionally we have a traditional design for all these kind of ducts. Hence, by using CFD, some popular approaches can be implemented and the duct design can be improved. As far as hydraulic is concerned, okay, so dam design, the pressure on the dams, and the split well, so or the pipes which are coming from the this one, particularly dams, that can be designed. Okay, submarine or the marines. So you can have design of ship, design of boat, design of submarine. All this kind of application can be designed, or even some cases we can have a design of or simulation of what you called as far as the the workstation, which are the oil refineries, which are working in the sea. So because of the sea air, what will happen to them? That can be evaluated. As far as oil and gas is concerned, so we see that number of tanks and all these things, they carry tanks where you can have partial filled, what you call as gas or oil or mixture of both. So when the truck moves, there is an interaction between this gas and oils. So usually known as sloshing of the liquids. Okay. Sometime it may happen that this motion may create the failure of that particular vessel. Hence, how we can simulate how the fluid can be moved by providing certain kind of motions. Okay. As far as power resolutions are concerned, we know there are n number of devices, n number of what you call as equipments are operating in the fluid power generation, starting from what you call as the thermal power plant, where we have a chimneys, boiler, air preheater, then heat exchangers, condensers, and whatnot, starting from turbine. Okay, so flow through all these kind of is been can be easily been simulated through this using CFD. However, till date, all this equipment is being developed by traditional approach. Okay, so there is a lot of scope for improvement as far as CFD is concerned. We if you use CFD, if you know the all data through these things, where the flow is happening, where the backflow is happening, where is the more resistance, all this data is available, then it will help us for designing a proper these things. Sports. Okay, this is one of my interested things. I have shown this one example of what we call as flow through over a hand particularly. Okay, the same hand is here. Okay, you can see that when the person swims, how we should swim, how the stroke should be done so such that the friction can be less, whereas the push given by the hand should be larger. Okay, so the stroke design, or even we can design what kind of clothes should be wear by that particular person so that it will have a less friction over a body. So even we can have a cricket example, we can have a football example. So I think you might ask one question: why the cricket ball is been polished only for the one half, not the other half is rough, whereas one half is smooth. The bowler and even fielder they try to push polish the things only in one side. Okay, so try to find these answers. Okay, so from my side, this is. I hope I am done within my time. Hopefully. So if you have a queries, please write to me, or even you can call me. You are most welcome. Okay,
Mm,
sir.
Sonawane, sir.
Yes, sir.
Yes. Uh, I found few questions from the chat box. Before that, I would like to ask one or two questions to you.
Yes, sir. Most welcome.
Uh, so you have shown many applications of CFD in different areas. It
Yes,
seems
sir.
that the CFD is very emerging field. Okay, but how do you see the features of CFD? What is
Uh,
the future?
yes, sir. As I told you, now the future of CFD is very much related with the future of high-speed computers. As you get more and more powerful computers, the speed of computer will increase, the data size will increase. Okay, so we are able to do more and more complex CFD numericals. So the future is very bright because we know that once the computers are going to evolve during the speed and size both way, and it's very easy for us to simulate a lot of examples which we cannot thought of those kind of examples.
Okay, sir, you might be knowing one of our students, Divyang Bora, who is present right now in this webinar.
Hello,
And
Divang. Okay. Yes, I know Divang.
on you know Divyang, he is working on absorption-based purification system, and
Okay.
he wants to know which tool is better for pressure drop analysis across porous medium.
A
Which,
tool, as far as tool is concerned, yeah, I got the questions. He want to
Mhm,
simulate the flow through porous media,
yes.
correct? Because as I told you, Navier-Stokes is the basic equations. When we want to add, say, more physics into it, say for example, if I want to add the multi-phase, okay, so I want to do something which will represent the multi-phase, okay, or if I want to do say multi-spaces, so I want to add some more equations into Navier-Stokes which will represent the what you call as multi-spaces equation. Similarly, for the porous, even ANSYS is also a good tool where the we can do the flow through porous medium. So he can try the ANSYS with the porous what you call as analysis.
Okay. So one of our viewers, I would like to see what is his name, Jerry Patel. Okay,
JD
he
Patel.
has, he has written that CFD analysis of machining process used like in wire cut EDM process. Okay, means it
Wire
is a
reading.
manufacturing.
Okay,
Yeah.
okay,
So,
okay.
okay. So, and I also would like to know that how the CFD is useful in manufacturing.
Yes, nowadays a lot of people are using a CFD in manufacturing. So, starting from you can say that the solidification, the casting. So they are trying to predict how the it gets solidified properly. Okay. Then you can have the tool cutting, for example. So tool
Yeah.
cutting,
Yes.
cooling particularly, how we can achieve the tool cutting with a minimum liquid. So that I think there is a one field called as minimum quantity lubrication, MQL, minimum quality
Oh,
lubrication or quantity
yeah.
lubrication.
Yeah. Yeah.
So people are trying to do that. Then we also have, as far as he is trying to say, manufacturing is concerned. So what kind of manufacturing you want to ask?
No, it's okay. The cutting fruits are used in the machining processes, and you have given
So
the answer.
even you can have the sintering process. Say for example, when you have a sintering, so sintering, say we have a furnace. So what will happen when you put all the insert in a, say particularly in a furnace? Are they evenly get heated? Are the sintering happening uniformly? So all this kind of analysis can be happened if you do the CFD of that particularly. Okay. So a lot of scope is there.
Okay, J.D. Patel is also the students at SBC Visnagar. He has written that. J.D. Patel, you might know. Yeah.
JD Patel, yeah.
Okay,
A lot
now
of
there
people
is
are
no.
there.
Yeah, a lot of people are there. Right now, I do not find any questions, so I would like to sum up this session by
Yes,
giving
sir.
the vote of thanks. Okay, first of all, I would like to thank today's speaker, Dr. Chandrakant Sonawane, for sparing his precious time for conducting this webinar for our students and faculty members. I also would like to thank our management and particularly to Babu Kaka and our principal, Dr. Latas Chaudhary, for providing such a wonderful e-platform for the students and learner to enhance their knowledge. I also would like to thank Professor V.C. Joshi and his backhand team for smooth conduction and handling of YouTube and Facebook live streaming without any disturbance. Last but not least, I would like to thank our students, faculty members, and other viewers who are continuously with us throughout this session. Thank you very much, and thanks to all once again. Thank you, Dr. Sonawane.
Yes, sir. Welcome, sir.